Good morning, future presidents. You guys are not very responsive. We'll work on that. So, a couple announcements before we get started. First off, I have to cancel my office hours today because I'm leaving on an airplane right after class. But the good news is, which is also my second announcement, is that all the GSI office hours are posted on bSpace, and they are all open for everyone. So you're welcome to go to any GSI office hours, not just your own GSI office hours. And I think those are pretty well scattered through the week in order to try to maximize availability for you guys. So check those out, and feel free to go to any GSI, not just your own. So sometimes it's good to get different perspectives from different people. Everybody has a different way of looking at these problems. So before we move on with today's topics, I wanted to discuss one more thing that is actually relevant for the last lecture, which is torques. And the example that I wanted to show was how scissors work. Okay. You might think scissors work because they are sharp, they cut things. Okay. Well, that's only part of the story. So that's the least interesting part of the story. So let me use my artistic abilities here and try to draw a pair of scissors. Whoop. Okay, that's pretty good for me, actually. Okay, so scissors. Scissors are another example of using mechanical advantage. And this time we're using the mechanical advantage to multiply the force that we're applying. So let's discuss that a little bit. So scissors, they have an axis of rotation, right? We've got two separate levers here. And in the middle, they're connected by an axis of rotation. So this is a rotation issue. So here's our axis. Of rotation. And in case you've never used a pair of scissors before, usually they're for cutting things, right? So let's say we have some object there that we're trying to cut. Okay? So how do scissors work? Well, they work through the application of torques. You are grabbing these scissors with your hand, and you are trying to squeeze them shut. So what you're doing is you're applying a torque to both of these blades around this axis of rotation. And so here is the force that you are applying. So you are applying a force on those two blades, trying to close them. That force is being applied with a lever arm. Okay, so you are applying a torque around that rotation axis to those scissors. Okay? So if there was no object there, then they're just going to rotate closed, right? But if you've got an object sitting here in the center of the blades, then it's going to be pushing back. It's applying its own torque back, okay, which is trying to counter the torque that you're applying. Okay? So from action-reaction, we know that if it's applying a force back on the blades are going to be applying a force back on it. So there will be a force here of the blades. Okay. That force is going to be acting with the little lever arm. So here is the lever arm on this side. Okay. And the point is, as you're squeezing those scissors closed, okay, until this starts to give, then there is no rotational acceleration, right? You're pushing down on it, it's pushing back until the point that it starts cutting through here. The fact that that is pushing back means that these are balanced, which means the torque on this side is the same as the torque on this side. So the force you're applying over this lever arm has to be equal to the product of those two. The force times the lever arm has to be equal to the force that the scissors are applying on this object multiplied by that little lever arm. Okay? So that means if this lever arm is much bigger than this one, that this force has to be much bigger than that one to counter it. Okay? So the scissors are effectively multiplying the force you're applying by the ratio of this lever arm to this lever arm. Okay? That's also why scissors don't work very well if you're trying to cut things that are way out here at the end, right? Because in this case, the lever arm is actually much longer on this side, which means the force that you're effectively applying onto that object is actually smaller than the force you're applying with your hand. So at that point, you're not getting any advantage from using the scissors. Right? So just another example of torques. Okay, let's move on with today's first topic, which is kinetic energy. So kinetic energy is the next form of energy we're studying. Okay, and this is just the energy of motion. We've already seen it in the class. Now we're just going to quantify it and talk about it a little bit more now that we also have rotational motion. So this is just the energy that an object picks up because it's moving with the speed. So when we had the pendulum, remember when we had the big bowling ball hanging from the ceiling, we saw how we gave it initial potential energy. That potential energy was converted to kinetic energy as it swung down to the bottom, and then it was converted back into potential energy. Okay, back into kinetic energy, back into potential energy, back and forth. Okay. So that pendulum, when it was swinging, had what we call translational kinetic energy. So it had energy from the fact that it had a speed that was moving. Right? It's not hard to imagine when we were spinning up that top yesterday, or on Tuesday, or if I'm spinning this wheel, that I'm giving it energy as well. This energy is energy of rotation. It's kinetic energy because it's the energy of something moving. Okay? But in this case, the energy is rotational kinetic energy. Okay? In the other case, it's translational kinetic energy from the fact it's got translational motion. Okay, an object when it's moving and rotating, like if I give this wheel both a spin and I let it translate along like this, right? It's doing both, right? It's translating, it's got a mass, it's moving in this direction with the velocity, but it's also rotating. So it has both forms of kinetic energy. Okay, so when we're looking at the total energy of this wheel, we'd have to count them both up. The translational kinetic energy and the rotational kinetic energy. Okay, let's just write down the formulas for those two so we can understand a little better how they scale. So for translational, kinetic energy, okay, we have the formula that the kinetic energy is equal to 1/2 times the mass times the square of the speed. Okay. If you want to know where this came from, this basically derives just by looking at the work we've done on an object. So if you look at the work, remember the work is the product of the force times the displacement. If you do the work on an object, you can calculate from the work how much energy we're transferring to it. And if you count that up, what you'll find is that this is the amount of energy that we've put into the translational motion from accelerating it. So the kinetic energy is just 1/2 the mass times the square of the speed. Okay, this factor is important. It scales as the square of the speed. So that means if you double the speed of an object, you quadruple the amount of kinetic energy that it has. Okay? An example which I think is given in your book, but I think it's a good example, is baseball and a baseball pitch. So a typical high schooler can throw, a high school pitcher that is, can throw a baseball at about 50 miles per hour. By comparison, the fastest pitch that's ever been recorded was, I believe, by Nolan Ryan, and it was about 100 miles per hour. So it's only twice as fast. So that might be a little surprising that Nolan Ryan, one of the greatest baseball players of all time, could only pitch about twice as fast as your average high school pitcher. But when you think about it in terms of energy, it gets to be a little bit more impressive. So twice the speed means that he was giving it 4 times the energy. Okay? So he was providing 4 times the amount of energy as a high school pitcher. So it's 4 times the kinetic energy. But that's actually not the only factor. So remember that kinetic energy is being provided by doing a force acting over a displacement. Okay? And the fact that Nolan Ryan was throwing that baseball faster meant that he was accelerating it for less time because the baseball was leaving his hand faster, it was moving faster. So it was twice the speed, so it's 4 times the energy, but it was only about 1/2 the time. Okay, because just because the ball's moving faster, so it's leaving his hands faster. Okay, so it's 4 times the energy over 1/2 the time means that it's 8 times the power. Okay, so that's a little bit more impressive. Nolan Ryan could provide 8 times the power of your average high school baseball pitcher. Okay, so remember all the analogies we did between translational motion and rotational motion last lecture? Well, it holds also for the kinetic energy. So rotational kinetic energy. It's the energy that basically an object has because it's spinning. You can probably guess if you remember our analogies. It's 1/2 times the rotational mass. Remember that depends on both the mass of the object and how the mass is distributed from the rotation axis. Okay? And then multiplied by the square of the rotational speed. Okay, so if you spin an object twice as fast, you've given it 4 times the amount of energy. Okay, so let's give some, I think, interesting real-world information, which will be important for the future presidents in this class. And that is the example of, well, I'm going to give one example, which is driving. So driving an automobile. And we're going to look at some of the energy that goes into that and how we can basically provide that energy for future applications. So, driving a car. Okay, driving. What do we do when we're driving a car? We're basically, for most cases, we are converting gasoline into the kinetic energy or potential energy of the car. So we are converting some form of stored energy into both kinetic energy of the car, so we're giving it a speed. We're also rotating the tires, so there is rotational energy that's involved. and potential energy if you're climbing any hills, okay, which we do a lot around this area. Okay, so driving is converting some form of stored energy into the useful kinetic energy and potential energy. Most of us, when we're driving these days, are driving using gasoline. And gasoline is kind of a very convenient form of energy storage, partly because it also is the energy source. Okay, so gasoline is the energy source, and it's the energy storage. And we release that energy, of course, by burning it. So that means that it's chemical energy. Okay, most other forms of stored energy, like batteries, or we're going to talk about flywheels in a second, the source of the energy has to come from somewhere else. Gasoline is different. Gasoline both provides the energy and it stores the energy. Okay? So it's a very convenient, a little too convenient way of getting energy into our cars. Let's talk about energy units, because we're going to talk more and more about energy as the semester goes along. So let's get some actual units down here. So we can start quantifying some of this. Okay, so we're going to use two main energy units in this class. There are a lot of energy units. There's probably, there's at least a dozen energy units that are pretty commonly used. So and converting back and forth between them can be a real pain in the butt. So we're going to focus on two of them. Both of them sort of give us down energy usage on sort of a personal scale. Okay, the two we're going to look at are kilowatt hours and calories. So kilowatt hours. So kilowatts is a measure of power, hours is a measure of time. Okay? We usually write that as just kilowatt hours, kWh. Okay? And this is the unit of energy that you will see on any of your electricity bills, if you guys have ever paid an electricity bill before. So this is sort of the scale of energy usage for houses and businesses, personal energy scale. So remember, watt is, if you've had any physics before, if you haven't, don't worry about this. Watt is an energy of power, is a unit of power, which is energy per unit time. So it's usually a measure of how much energy we are transferring or using over time. So it's a rate of energy usage. Okay? And to give us a little bit of scale here, let's use the most common example that we have, which is a typical light bulb. This is one of the most common ways that we use energy. A typical light bulb in your house, well, it can range from anywhere from maybe 60 watts up to 100 watts, but a typical light bulb is on the order of 100 watts. That's for sort of a bright light bulb like you might have in a kitchen or in a brighter lamp. 100 watts, remember 100 kilowatt would be 1,000 of these, so 100 watts is equal to 0.1 kilowatts. Okay. So that's the rate of energy use for a typical light bulb. Okay. And when this bulb is on for 1 hour. So when it burns for 1 hour, then the amount of energy that it used is 1 kilowatt hour. Sorry, it's 1.1 kilowatts hours. Okay, so 0.1 kilowatts, it's the energy per unit time. You multiply it by 1 hour, and you get 0.1 kilowatt hours, okay, is used in that 1 hour. Okay? So that's for a typical light bulb. So if we have 1 kilowatt hour, so 10 times larger, then we're talking about either the same single light bulb on for 10 hours, or we're talking about 10 light bulbs on for 1 hour, right? So either 1 for 10 hours or 10 for 1 hour equals the same amount of energy that is used. Okay, so I think that kilowatts and kilowatts hours give us sort of a good scale for the world around us, okay, for the type of energy we use in our everyday life. Let's compare that to a person and the amount of energy that you need as a member of the human race just to survive. Okay, so for comparison, okay, a person needs on the order of 2,000 calories each day to survive. Some people need more, some people need less, but that's the right scale. Okay? That energy, of course, is usually provided by chemical energy. In this case, in the form of tasty food, hopefully not gasoline. Okay, so, but it's still chemical energy. Our body is effectively burning that food in to release the energy for it. Okay, 2,000 calories is equal to 2.4 kilowatt hours for comparison. Okay, so a typical diet, okay, the amount of energy we need to survive is about 2.4 kilowatt hours. Okay. Remember that a light bulb is about 0.1 kilowatts. Okay. So that means that 2.4 kilowatt hours, remember, is equal to 0.1 kilowatts times 24 hours, okay, 24 hours in a day, which means that you, my dear student, are a very bright light bulb. Okay. Typical person uses the same amount of energy as a 100-watt light bulb. That's your energy requirement for a day. Okay. You are a bright light bulb. Be proud. Okay, so just so you know, 2,000 calories, a typical diet requirement. You can get that through about 1 pound of potato chips, or if you're a little better eater, that's about 20 apples. Okay, for comparison. So however you choose to get your calories, your energy intake is your choice. Okay, so this gives us an energy scale we can start working with. Let's go back and talk about our car and gasoline and how much energy is actually stored in a gasoline tank. So let me start a little table over here. Just for discussion. Okay, car has to travel for long distances, which means that it needs an energy source. That means we have to store energy in the car, okay, for it to be accessible for converting to its kinetic energy and its potential energy. So let's look at some possible ways of storing energy in the car, and let's look at how much energy we can actually store in that. So for comparison, so we're going to look at the different storage mechanisms, and we're going to look at the energy content. Okay, so we're going to use funny units here. When you're talking about gasoline, we normally think about gallons because we have not quite converted to metric standards, but we can always convert later. Let's talk first about gasoline. How much energy is stored in gasoline that's available for our use in the automobile? If you count it up, there are about 13 kilowatt hours per kilogram of gasoline. Okay, and that is just the fuel, doesn't include the mass of the engine. So for each kilogram of gasoline that we burn, we can get out 13 kilowatt hours. Okay? So a kilogram, not such a common unit, but a kilogram, there are about 3 kilograms in each gallon of gas. So for a gallon of gas, you would multiply that by about a factor of 3. Okay? So there's closer to 40 kilowatt hours per gallon. Okay, this is looking completely at the gasoline as a way of storing the energy. Okay? And we get that out by burning it. Okay? The gasoline also, like I said earlier, provides the energy. Okay? The gasoline under the earth is a natural storage of vast amounts of energy, so it's kind of convenient for that. We don't need another source of energy in order to get stored in the gasoline itself, but we're going to compare it here as a storage mechanism. For comparison, lead-acid batteries. So these are getting replaced quite often, but these have been sort of the standard battery technologies for, well, since we've had batteries until the lithium-ion batteries have been taking their place. But lead-acid batteries, that's a typical battery you buy at the grocery store. It's a typical battery in your car. By comparison, the amount of energy that you can store in a lead-acid battery is very small, about 0.04 kilowatt hours per kilogram. This is the main reason we don't have a lot of battery-powered cars around. Okay? It's because batteries don't store nearly as much energy as gasoline does by itself. So in this sense, gasoline, unfortunately, is an extremely convenient method of storing energy in our cars and being able to access to it, because there's a very large amount of energy. So that's a factor of 10, 100, very large factor, a few hundred times as much energy that's stored in a given mass of gasoline as opposed to a battery. If we come up to the current decade at least, lithium-ion batteries by comparison. These are batteries that are in your laptop. They're in the, I think this is what they use in the Priuses, but I'm not sure, hybrid cars. But this is certainly the cutting edge of battering technology, at least for widespread use. It gets a lot better. So it is 0.13 kilowatt hours per kilogram. So much better than lead acid batteries, but still a factor of 100 below gasoline. Okay? So it still takes 100 times as much mass of lithium-ion batteries in your car to go the same distance as it does for a tank of gasoline, okay? Which is extremely prohibitive in terms of the how far just pure electric-powered cars can travel, right? Just from the sheer amount of mass you have to have in batteries in order to provide the power. Okay, let's look at one more option, which are flywheels. So flywheels are, you can think of them as just tops, right? Massive discs, okay, that we can spin up, just like we spun up that top yesterday and we got it moving fast. Okay, if we spin up a flywheel and get it going really fast, it is storing energy. So it is a method of storing energy in the form of kinetic energy, but in a compact location. So we've got this massive wheel that is spinning. Okay? And let's look at comparison, how much energy we can store up in that. We can reach, by comparison, in the flywheels, so here we're talking about, I'll talk about this in just a second, but we can reach storing energy in flywheels about 1.8 kilowatt hours per kilogram, okay? Which is a really major improvement over batteries. So it's actually technically possible. So that is still not as much as gasoline. Okay? It's still almost a factor of 10 below gasoline. But it has a different advantage as well, which is gasolines require really heavy engines, right, in order to burn the fuel. And if you go to flywheel technology, you can get rid of the engine completely. So you're actually saving a lot of mass in the car. There's other advantages as well, which we'll talk about in 1 second. So, so the basic idea about a flywheel is very simple. We just have some large mass. Remember, it's kinetic energy. It's equal to 1/2 times its rotational mass times the square of its speed. Okay, so all we want to do is take this large mass and spin it up really fast. Okay? And if we do that, we've got a nice store of energy there. So this is kind of a simple concept of what a flywheel looks like. We know from our discussion of rotational mass that you probably don't want a single solid mass. You probably want the mass distributed around the edge because it'll have more rotational mass the further out that the mass is distributed. Okay? And you might want to break this up so that if we have we have spinning mass in something like an automobile, that we don't store that in one giant mass spinning really fast, but we store it in lots of small masses spinning. Okay? But the limit on how fast we can spin something this comes from when it starts breaking apart, right? At some point, you're going to be spinning it so fast that it's not going to be able to hold the tension you're putting on it, and it's just going to fly apart. You might think that steel is the best option for flywheels, but actually steel breaks apart a little too easily. So there are a lot of new carbon fiber composites, new technologies that are letting you get to reach these type of energy densities. Okay, so let's just do some number comparisons here. So 12 gallons of gas, what's in a typical car? Okay, 12 gallons of gas hold about 430 kilowatt hours of energy. Okay, so for comparison, if we had a really advanced flywheel, okay, that could hold this much density, we would need a flywheel of about 240 kilograms to store that energy, okay, in a car. That seems like a lot, okay, but the flip side is that we can get rid of the engine potentially if we go to a whole flywheel system, so it actually saves a lot of mass. Okay. The perhaps scary thing about this is that flywheel needs to spin at about 20,000 revolutions per minute, which is fast. Right? That's very fast. Okay. But that's okay. We can do it. We're a modern technological society. Modern flywheels are getting up to spinning this fast, no problems. Okay? And they don't fly apart because they're using very strong materials, carbon fibers. Okay? It's not a crazy idea. The advantages of flywheels are several, and the disadvantages are several. Let me write down some of the advantages and disadvantages. Okay, so the advantages of flywheels as technology for storing energy is, first off, they are very efficient. We can get the energy back out of them very easily. So we can get back out about 90% of the energy that is stored in the flywheel and convert that to kinetic and then potential energy for the cars. So by comparison, burning gasoline, we'll get to this later in the semester, gasoline engines, by comparison, are only about 20% efficient. Okay? So that actually helps a lot, because that means that even though we can't store as much energy in something like a flywheel, we don't waste 80% of it getting out. We only waste 10% of it, okay? Which means that we really only need about 50 kilograms of a flywheel to match a full tank of gas. Okay? So when you take the efficiency into account. So that's getting down to pretty reasonable mass scales for something like an automobile. Okay? Other advantages, there's no engine. The flywheel is storing the gas, and storing the fuel. It's pretty easy to get out, so you get better mileage. It's quiet. Okay. There are no emissions from the flywheel, so unlike a gas car. And there's a couple other technical things. One is it's very low maintenance, so it's a lot cheaper to maintain. You just got a big, heavy mass that's spinning. Okay? It's much lower maintenance than, for example, batteries. And there's a couple other things which are, it's very easy to charge up a flywheel to get the energy into it and out of it. Batteries have a natural rate at which energy can be put into them or out of them. If you go over that, they tend to explode. Not a good thing. So one of the big issues facing electric cars, for example, is charging them up. Let's say you're going on a big long trip and you need to stop for fuel, which is charging up your batteries. Then charging up, for example, the batteries in a car might take 10 or 12 hours. Right? So there are potential ways about getting over that hurdle, like maybe you don't charge up batteries. Maybe the gas stations of the future just have big stores of already charged batteries, and you just swap them in and out of your car. Okay? But if it takes 12 hours for you to charge up your batteries once they get low, then that's going to be kind of a downside to going to electric cars. So the flip side of that is for flywheels, you could charge them up very rapidly. There's no limit on how fast you can put the energy into them. So you could easily charge up the flywheel in 5 minutes and get the energy stored in there pretty quickly. Okay. The disadvantages for a flywheel? Well, you've got a really rapidly spinning masses there. And the flywheel, the limit on flywheels is that if they spin too rapidly, they can break apart, right? And so suddenly you've got very fast stuff flying everywhere. Not a very good scenario. Okay. The carbon fiber flywheels actually get around that problem quite a bit because they naturally break up into tiny little fibers. Okay? So instead of breaking up into big massive chunks that would go flying elsewhere, so by the way, this might also happen if you get in an accident, right? Get in an accident and suddenly your flywheel gets hit and breaks. So in this case, the composite materials like the carbon fiber will break into little tiny shreds. You got little tiny pieces that are flying out. They're actually really easy to stop. So your flywheel will just be encased in a little bit of shielding and be able to stop it, no problem. The other potential problem with flywheels, remember the suitcase that I was carrying? Remember when I tried to turn? You imagine going around a corner with your car and suddenly your back end starts picking up? Okay, that's okay. You have two flywheels, one going one way and one going the other, and they balance each other out. Right? The way actually most flywheel technologies work that would be going into automobiles is that you have lots of flywheels. So lots of them, and they're balanced out, some going one way, some going the other. And as long as you can keep those balanced, then you don't have any problems with that motion, the gyroscopic motion, which we'll be talking about in a couple weeks. Let's see, I need my laptop. Okay, I just want to show you guys a couple examples of these. No, I don't want to not now. Okay, so one of the reasons I want to talk about this is because, let's see if I can get this running. These technologies are actually making their way into, oh, the sound came on, great. This is Volvo. Volvo proposed earlier this year that they're going to start the development of flywheel hybrids. So this would be like the Toyota Priuses, except for they use this big flywheel there spinning. So the way hybrids work, like the Toyota hybrid, is that it has a relatively very small battery. It's not required to carry all that energy. All it requires is to store the kinetic energy that the car is losing as it comes to a stop. So I love that. Isn't that nice music? Okay, so Volvo is at least contemplating producing these flywheels. So as you see, as the car is coming to a stop, the flywheel engages and it basically picks up the kinetic energy that the car is losing and stores it, and then it will, when the car wants to accelerate, it pulls the energy first out of the flywheel and moves it back up, and then the engine would kick on. So this is how hybrids work, is that they have a small storage capacity, and all that really needs to store is just that transient energy that you pick back up from stopping the car. Okay, This, unfortunately, these are called flywheel kinetic energy recovery systems, and they have an extremely unfortunate acronym. There. I'm guessing Volvo will change this. Oh, by the way, so these actually, so Volvo is putting this technology in its cars, but these are actually already working in Formula One racing cars. So let's see. Ferrari, Renault, and BMW are already using these in their race cars, and the goal is to develop technology for their commercial cars. So you guys will probably be hearing more and more about flywheels over the next few years. This is a really interesting example. This is a promotional video.
Take an advanced carbon fiber rim, lift it on magnets in a vacuum, spin it at very high speeds, and you can store electrical energy. The Smart Energy 25 flywheel system from Beacon Power.
I'm not trying to sell or do anything with Beacon Power.
It's the core component of our Smart Energy Matrix, a 1 megawatt energy storage system that makes power grids smarter, more stable, and more efficient, with no fossil fuel consumption or CO2 emissions. The system can be expanded and built out to 20 megawatts or more, recycling electricity quickly and reliably, storing excess power and giving it back when needed to balance the grid's supply and demand, and support the deployment of wind and solar power. Clean and efficient energy storage, built with Beacon Power flywheel technology.
More good music. Okay. So I showed you this. This is really interesting to me. So Beacon Power is a company on the East Coast, and they just earlier this year opened up a 20 megawatt energy storage facility using these flywheels, these big massive flywheels you saw there. So one of the real challenges of clean energy sources like solar and wind is that, for example, solar power only is provided during the daytime, but we need power at night. And wind power is only provided when the wind is blowing, okay? But we need, for both of them, one of the big challenges for implementing them on large scales is developing storage facilities for the power. So some people are doing this, proposing to do this by building really giant banks of batteries. So there are companies that are making big train cars filled with lithium-ion batteries. So, and this is another, I think, really interesting example. And the fact that it's just been, the first facility of this type has been built earlier this year is, I think, looks really promising. So, okay, so guess what time it is? Well, my computer's up. Let's go ahead and have our quiz for today. Quiz slips, yes. Who doesn't have a quiz slip? Raise your hand, maybe you have a nice neighbor. Okay, anybody still not have their slips? Put your names on it, please. Put your date. Today's the 8th, right? September 8th. Okay. Let's get started. Question number 1. When chewing hard nuts, we use the teeth towards the back of our mouth, our molars, because we are able to exert greater A, force, B, torque, C, angular velocity, or D, lever arm on the nuts. Why do we chew things at the back of our mouth that are really hard instead of at the front of our mouth? Okay, question number 2. When building soapbox cars, which race by coasting downhill, it is better to have solid wheels rather than ones of equal mass with spokes. So, what type of wheel should we have on a soapbox car? If you don't know what a soapbox car, then you're making me feel really old. It's just a box that has wheels attached to it. It's like a wagon. So it just rolls down the hill with the kids can ride in. Okay, the question is, what type of wheels should it have? A, solid wheels have a lower rotational mass and therefore accelerate faster. B, solid wheels are easier to paint. C, the solid wheels have a higher rotational mass and therefore retain more rotational energy. And D, the wheels with spokes lose too much energy by heating up the air. Spokes, so spokes. Sorry, great question. These are spokes. The little bars that come out to hold the wheel. So the question is it better to have a wheel like this where the mass is concentrated on the edge? Okay? Or is it better to have a solid wheel, so one solid piece? Like this. By the way, the goal implicit in this is to win the race by going faster. Ouch. Oops. That's kind of a tough question. Okay, let's go ahead and, you didn't get that yet? Yes? And let's pass that over toward the edge. Okay, the geosides will come up the sides and collect those. Okay, let's move on. We're going to talk a little bit now about friction. We've already talked about friction quite a bit, but I wanted to spend a little bit of time developing our knowledge on how friction actually works. So friction, we all have a somewhat intuitive idea of what friction is, but let's just qualify a little bit more detail. So friction is a force between two surfaces. Okay? And specifically, it's a force between two surfaces that opposes slipping between the surfaces. Let's write that down. That's a force between two surfaces. And it opposes opposes slipping between the surfaces. I think that part is pretty intuitive. Okay, empirically, I think, all know that the rougher two surfaces are, that the higher the friction will be between the surfaces. I think another thing which we kind of know, even though you might never have thought about it, is that the friction is higher the harder two surfaces are pushing together, right? So if you just even think about the friction between your hands, when you're sliding them back and forth, okay, there's a little bit of friction there, but it's not too bad. Okay? But if you really push on your hands, right, the friction gets stronger and stronger the harder that you are pushing them together. So the more force that two surfaces are pushed together, the larger the friction is between them. Okay? And the friction is the force that's trying to keep them from slipping over each other. Okay, what might not be so, I think, intuitive is that there are actually two types of friction. There's static friction and slipping or sliding friction. Okay, static friction versus sliding friction. Static friction is friction that keeps two surfaces from starting to slip in the first place. Okay, so let's see if I have a good object here. I don't have a great one. Let's use these. Okay, so this is sitting here, and I'm going to start pushing on it. Okay? If I start building up the force, okay, it takes a certain amount of force on my part to start it sliding. Okay? When it's not sliding, I'm still exerting a force on it, but the frictional force is pushing back. Okay? But there is no slipping, right? It's sitting there still. That's a static friction. Okay? And then if I push it hard enough, it starts to slide. Okay? And then there's also friction, but that's friction actually between the two surfaces as they're slipping over each other. So the difference between those is that once it starts slipping, there's basically a constant force, frictional force, that is acting back on it. The static friction is different, though. Right now, it's just sitting there. There is no static friction on that. I'm not applying any force that's trying to make it slip, so there's no frictional force to counter that. Okay? If I push on it a little bit, the static force starts pushing back, okay? But it only pushes back as hard as I'm pushing on it. Okay? So it's not pushing back any harder. If it were pushing back harder than I was pushing on it, then this would go moving in the opposite direction. Okay? So static friction opposes relative motion, but the magnitude of it is basically what it needs to be to oppose that motion. Whereas once it starts slipping, okay, it will experience a constant frictional force. Okay? The heavier it is, so if I put more masses on here, so it's got more of a weight pushing down the table, the normal force is higher, okay, the friction increases, and it just increases proportional to the amount of weight that's on there. Okay? If I push down on it really hard, there's even a much stronger force connecting those two surfaces, right? And then it takes a lot of force for me to start this moving. Okay? So, static versus friction. Let's see, can I get the projector for just a minute? Let's see, this went to sleep. Let me. Okay, the computer's on. Let's see, where is this going to show up? There it is. Okay, great. So, another thing that's not totally obvious about friction is that static friction is generally larger than slipping friction. So that means it actually takes more force to start something moving than it does to keep it moving. So I'm going to apply a force onto this mass. Okay? I'm going to be pulling it towards the right. First, it's feeling static friction. Okay? At some point, I'm going to give it enough force that it's going to slip. Okay? And then once it starts slipping, it's just going to be measuring, it's just going to have sliding frictions. Okay, so let's go back to the computer. So, there we go. So this is going to be measuring the force over time. So when I turn this on, you're going to see on the red line the force that I'm applying, and so you'll see it going up, and then this axis is just time, so we will see the plot going on. And let me do it once, and then I'll show you what we're looking at. Okay, so let me start this. Okay, so I'm going to start pulling on this. Okay, and what you can see if you look very carefully, this isn't a great example. Let me do it once more with more mass on it. I think it'll be more obvious. Okay. Okay, it's not the cleanest plot in the world, but you can see up there if you look that as I started pulling, I had to increase the force on it, okay, to get it to the point where it started slipping. So that's where it's going up here on the left, and it peaks. Okay. Once it starts slipping, you see the force goes down. That's because it started sliding and the force decreased. Now, I didn't pull it at a very constant acceleration, but you can see over here on the right that the level of the force I was applying was pretty constant. Okay, the slipping force was basically a constant amount, and it was less than the amount of initial force, static force, that I needed to apply in order to get it to move. Let me try that one more time, see if I can make a cleaner plot. Okay, that was a little better. Okay. You see, I had to give it an initially more force to get it to start moving. So that's that little peak here on the left. And then once it started slipping, I could give it basically a constant force to counter the friction. Okay, but it was less force than I needed to get it to start moving in the first place. Okay. That's the difference between the static force and the frictional force. You can also see that that I had to keep increasing the force to the point where it started slipping. Okay? And then the static force, which is what's being measured up here, it was increasing as well to the point where it started sliding. Okay? Static force is only what it needs to be in order to keep the relative surfaces from slipping. Then once it starts slipping, it turns into sliding friction, and it's basically a constant. Sliding friction doesn't depend on speed, actually. So once it starts slipping, the frictional force that it measures doesn't care whether it's moving very fast or moving very slow. Okay. So that's why, like when you're sliding objects, like if you've got a heavy box and you're sliding it on the floor, you have to push it really hard to start it moving. But once it starts moving, you actually can lower down your force and get it going. That's because it's changing from static friction to sliding friction. And I already showed this in a lecture a couple times ago, but I wanted to reiterate this again. So we've got two blocks here, right? So if I give it a push, friction on that table is pushing backwards, and it's resisting the relative slipping motion. Right? But remember, there's also friction between the two blocks, right? And it's the frictional force of the bottom block on the top one that's actually accelerating the top block. So friction is not just a dissipative force. It doesn't just dissipate energy. It's actually a pretty key component to motion in general. It can accelerate objects or it can slow them down, is the key point. Friction also is a force. So it's always an action-reaction pair, remember. So when I push on that, there's a frictional force pushing back on the table, trying to resist that motion, but that means that there's a reaction pair of this pushing on the table, which is trying to push the table forward. Okay? So frictional forces always come in action-reaction pairs. Okay, let's see. We're going to start talking about wheels. Let me get these two. Let me do the two of these demos up front. So we won't have to pull these out next time in case we run out of time. So let's see. Can you focus down here? Okay, so I'm going to be working just in this area right here. Okay, so we got two wheels. Okay, sounds like our quiz problem, number 2. I've got 2 wheels. These are on our fulcrum. We learned about fulcrums last time. You see they have their equal mass. Okay. And I'm going to let these wheels roll down this plane. Okay, so I'm just going to start them from rest and let them move. Okay. And let's see how their motion varies. Oh, I think I gave it a little bit of a push. Let me do that again without cheating. Okay, so I'm going to let them free. And let's try it again. Okay, you can see that they're not rolling down with the same speed. Okay, one of them's accelerating faster than the other one. Okay? And that's because even though they have the same mass, they have different rotational masses. Okay? You can see that better from the back. Okay? These are 2 wood blocks, but they both got metal added onto them, which is affecting the rotational mass. This one has this, I think this is brass, so this brass plug in the center, okay, which is putting more of its mass near the rotation axis. Okay. This one has the brass, it's a ring around the edge, so the bulk of its mass is located on the outside. So we know from the definition of rotational mass that this one has more mass located further away from the rotation axis, so it has a larger rotational mass, which means that it is going to be harder to rotate that one than this one, which means that when we let them go, the one with the smaller rotational mass is going to start rolling faster. See, whoop. I need a bigger board for this. It's too narrow. Okay. Likewise, I know this is not going to work, but I'll try it anyway. Let's give them a same velocity rolling up the plane. Okay. And if I were really good aim and this board were a little bit wider, then we would see that if I start them off with the same velocity and give them a push, this is so going to fail. Okay, if I give them a push, that worked a little bit. You saw that this one rolled up higher than the other one. Okay? So I'm not going to be able to reproduce that, but let me do it. Let me try. So, yes, sort of. This one rolled up higher. This is the one with the larger rotational mass. So when I give them both initial kinetic energy here, so I move them actually with the same speed. Okay, so that means they're rotating with the same speed. This one has a larger rotational mass. So even though the speeds are the same, remember the kinetic energy is 1/2 the rotational mass times the square of the angular speeds. So that means this one has more kinetic energy. Okay? So that means when I push them up at the same speed, this one has more energy stored in it than the other one does, and it's going to roll higher in theory, if I can do this right. It's going to roll higher up the plane. I'm not going to be able to reproduce that. This one rolls higher up the plane than that one, okay, even though it has the same speed, because it has more energy stored in its rotational mass. Okay, rolling. Wheels. Let's start talking about wheels. We probably won't get through all of this, but we will get through part of it. Okay, we all know that wheels are a very convenient way to move things, and let's talk about why. Okay, for an ideal wheel, so an ideal wheel is a hard wheel, so not a soft wheel. So for a hard wheel on a hard surface, the friction is 0. Okay, that is not very intuitive. Okay. The reason that a wheel will roll much further than a box will slide is because the friction acting on a wheel, when it's working properly, is 0. Okay. That is why objects roll much further than they will slide. So in a normal motion for a wheel, the wheel is rolling without slipping. Okay, and let's talk about that a little bit. Let me show you what happens to a point on the wheel when it comes down and touches the ground. So, actually, I'll do that on the back one there. Here we've got a wheel, and I'm going to take this piece of chalk and put it right on the edge. Okay? And so I'm going to roll it on this board, and on the blackboard what we're going to see is what happens to this point as the wheel moves forward. So you can see that as I'm rolling it, right, that point is moving forward and it's coming down. It's touching the ground and rolling up. Let's look at how that looks. If I can do this carefully. Okay. Kind of a slow wheel, but that's okay. The point is to do this neatly. Okay, look what happened to that point. That point of the wheel came down, touched the ground at one single spot, okay, and lifted right back up. Okay. So this shape that this is called a cycloid. You don't need to remember that, but that's what it's called. And the key point to remember, though, is what happened to that point, which is that single point of the wheel that was contacting came down, vertically touched the ground, lifted right back up, and went up. Okay? The point of that is that there was no slipping here. That was the point of contact of the wheel, and it wasn't trying to move back and forth. It was literally coming straight down, touching the ground, and lifting back up. There was no slipping back and forth, so there was no friction. Okay, now wheels don't have to work this way. Let's give you two counterexamples of that. So first off, let's say, so here's our wheel, and let's give it a translational motion but no rotational motion. Okay, so this would be a wheel that is not functioning very well. So I'm just going to start giving it a translational motion. Let me put it down and touch with the floor. Okay. And it starts rolling, right? So why does it start rolling? We come down, it's got relative motion, so when it touches, there is slipping here. That wheel is trying to slip over the surface. The fact that there is friction, okay, it's slipping means that there's friction. That friction is acting backwards. It's providing a torque on the wheel, and so it starts to angular accelerate the wheel. Okay? So to the point where it starts rolling. Okay, so it is the frictional force that is starting to rotate that wheel, right? But I would claim it's rotating it just to the point where it starts moving, rolling, and then it stops. Let me draw the picture of that. Don't fall. So here is this case, which we've got the wheel. I'm giving it a velocity. Okay. It's not rotating initially, so that means this point, which comes down in contact with the ground, is going to start feeling a frictional force, so this is sliding friction acting backwards. Okay. We've got a force, we've got a lever arm from the rotation axis. That means we have a torque, and so that frictional force is going to start rotating, right, spinning up. Okay, let's do a counterexample, which is I'm going to give this wheel not a translational velocity, but a rotational velocity. Okay. And I'm going to then put it down on the ground, and let's see what happens if I do this carefully. Right. So of course, it starts taking off, right? It's got rotational velocity. I set it down. Okay. And the frictional force with the ground starts it moving. Okay. But in this case, let's draw this picture. I'll draw that one here as well. We're starting this off with a rotational velocity, so this wheel is spinning. Okay. We're going to set that down on the ground, and in this case, which way is the frictional force? Let's look at that again. So this is spinning in this direction. The point that comes into contact is actually moving backwards, right? So the wheel is going this way. So the slipping between the surfaces is that the wheel's is sliding this way, which means the frictional force is in the forward direction. Okay? So in this case, the friction is acting in that direction. So the frictional force is pushing it forward. Okay, so that's if the wheel is slipping. So if it's moving like this, if it's spinning too fast and you put it down, the frictional force will try to accelerate the wheel to the point where, so that it's moving forward faster in this direction. Likewise, if it's not spinning at all, and we set it down, we give it a translational velocity, the frictional force goes in the opposite direction. Okay? A normal wheel, when it's operating and not slipping, is the balance of these two. The frictional force, if it's rolling too fast, the frictional force will speed it up. If it's rolling too slowly, the frictional force will slow it down. Okay? For normal rolling like this, each point in the rim is coming down, touching the table, lifting back up, and there is no slipping between them. It's not slipping forward or backwards. Okay? And when a normal wheel is rolling without slipping, there is zero friction. Okay? We will pick up there next time and talk about accelerating this wheel.